Let's explore quality of service, often called QoS. This involves traffic prioritization and service guarantees on a network. We will understand how networks manage different types of data to ensure important applications perform well. So, what exactly is quality of service? Quality of service, or QoS, refers to the ability of a network to provide different priorities to different applications, users, or data flows. It guarantees a certain level of performance to a data flow. Here are some key concepts to understand. First, traffic prioritization is based on importance. Second, resources are allocated for critical applications. Third, bandwidth management and guarantees are put in place. Fourth, latency and jitter are controlled. And finally, mechanisms are present to prevent packet loss. Businesses need quality of service for several important reasons. Let's explore some use cases. First, consider real-time communications. Voice and video applications require consistently low latency and minimal jitter to maintain call quality. Examples of these are Voice over Internet Protocol, or VoIP, video conferencing, and telepresence. Next, consider critical services. Mission-critical applications need guaranteed bandwidth and priority over less important traffic. Some examples of this are healthcare systems, financial transactions, and emergency services. Finally, media streaming is a very important use case. Streaming services require consistent bandwidth to prevent buffering and maintain the quality of experience. Examples here are video streaming, online gaming, and live broadcasts. Key quality of service parameters need to be monitored and managed. The first parameter is bandwidth. Bandwidth is the maximum rate at which data can be transferred across a network connection in a given amount of time. Bandwidth determines the overall throughput capacity. Next, let's discuss latency. Latency is the time delay between the moment data is transmitted and when it is received at its destination. Latency is critical for real-time applications. Now, what about jitter? Jitter is the variation in latency over time among data packets from the same source to the same destination. Jitter affects the quality of voice and video. Finally, we have packet loss. Packet loss is the percentage of packets that fail to reach their destination during transmission across a network. This degrades application performance. Let's take a look at the different mechanisms that enable quality of service. The first thing is classifying and marking traffic. This involves identifying and categorizing network traffic based on attributes like source and destination, protocol, or application type. Next comes packet marking. This means tagging packets with priority information using fields like Differentiated Services Code Point, or DSCP, or Class of Service, or CoS. After this, traffic needs to be managed. This involves queue management, which means organizing packets into different queues based on their classification and applying specific handling rules to each queue. Lastly, we need congestion avoidance. These are techniques like random early detection, or RED, that proactively drop packets when congestion begins to build to prevent queue overflow. Let's take a closer look at some quality of service scheduling mechanisms. The first mechanism is priority queuing, or PQ. In this system, packets in higher priority queues are always transmitted before packets in lower priority queues. It is simple but can lead to starvation of lower priority traffic. Next is weighted fair queuing, or WFQ. This allocates bandwidth to different traffic classes based on assigned weights, ensuring fair access while still prioritizing important traffic. Finally, class-based weighted fair queuing, or CBWFQ, extends weighted fair queuing by allowing traffic to be grouped into user-defined classes with specific bandwidth allocations. Let's explore quality of service models. We will begin with integrated services, or IntServ. This is a fine-grained quality of service model that provides guaranteed service levels by reserving network resources for specific traffic flows. Features include resource reservation for each flow, a signaling protocol, or our SVP, for path setup, guaranteed service levels, and admission control mechanisms. It is best for small networks with critical applications. Now let's move on to differentiated services or DiffServ. This is a scalable quality of service model that classifies traffic into a limited number of service classes and provides different levels of service to each class. Features include class-based traffic handling, DSCP marking for packet classification, per hop behaviors or PHBs, and it is scalable for large networks. It is best for large enterprise networks and service providers. Let's walk through the steps to implementing quality of service. First, you need to identify traffic types. Analyze network traffic and categorize applications based on their requirements and business importance. Next, define a quality of service policy. Create a policy that maps traffic types to service classes with specific bandwidth, latency, and priority requirements. After that, configure classification and marking. Set up traffic classification rules and mark packets with appropriate DSCP or QoS values at the network edge. Finally, implement queuing and scheduling. Configure queuing mechanisms and scheduling algorithms on network devices to enforce the quality of service policy. Let's learn how to monitor and troubleshoot quality of service. Here are some monitoring tools. First, NetFlow collects Internet Protocol, or IP, traffic information to monitor bandwidth usage by application and traffic class. Second, Simple Network Management Protocol, or SNMP, gathers statistics from network devices to track interface utilization and queue depths. Third, Internet Protocol Service Level Agreement, or IPSLA, measures network performance metrics like latency, jitter, and packet loss in real time. Finally, Quality of Service Management Information Bases, or Quality of Service MIBs, provide detailed statistics on quality of service policy implementation and effectiveness. Here are some troubleshooting steps you can take. First, verify quality of service configuration with Show Policy Map interface to confirm policies are applied correctly. Second, check traffic classification with Show Class Map to ensure traffic is properly identified. Third, monitor queue statistics with Show Queuing interface to identify potential bottlenecks. Fourth, use packet capture tools to verify DSCP markings are preserved end-to-end across the network. And finally, analyze application performance metrics to validate quality of service effectiveness and adjust policies as needed. Let's go over some quality of service best practices. First, maintain end-to-end consistency. Maintain consistent quality of service policies across the entire network path to ensure service guarantees are preserved. Next, limit the traffic classes. Use 4 to 8 traffic classes to balance granularity with management complexity and network overhead. Establish clear trust boundaries where quality of service markings are applied and enforced to prevent misuse. Finally, regular monitoring is critical. Continuously monitor quality of service performance metrics and adjust policies as traffic patterns and business needs evolve. Effective quality of service implementation ensures critical applications perform reliably even during network congestion. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.